Because of the uncertainty that's inherent in hypothesis testing and the hypothesis testing framework, it's always possible that when we're making hypothesis tests or when we're drawing conclusions from hypothesis tests, that we get something wrong, that we make a mistake, that the data are actually, supporting one hypothesis, but we conclude that they support another. And these mistakes are going to be a naturally arising because of the fact that there's inherent uncertainty, right? So in order for us to still trust the results of hypothesis tests and to recognize that there is some level of uncertainty in these conclusions, but that, it's sort of the best that we can do, in order for us to sort of still proceed with hypothesis testing, we need to understand these types of mistakes. We need to understand what could possibly go wrong. And then we need to understand how we get choices in order to control the likelihood of these mistakes so that we can balance out how acceptable is a mistake. And if it's very unacceptable, then we can lower those probabilities. And if it's acceptable, or at least somewhat more acceptable, then we might be able to sort of draw stronger conclusions in a sense. So every hypothesis test has to be run for some fixed level of significance. We need to define what is that level of significance, and then the conclusions that we draw are going to be predicated on that level of significance. And that level of significance needs to be selected based on the specific context of the problem at hand. Now, when we're selecting the level of significance, the primary consideration that we're going to be giving to the level of significance that we're selecting is how acceptable are different kinds of mistakes. And so we need to understand how is the level of significance tied to these types of mistakes, and also what are the different types of mistakes that we might be making. So to first begin, we'll dive a little bit deeper into the level of significance itself. And so we denote the level of significance using alpha, and the level of significance, broadly defined, is the amount of evidence that's required in order for us to reject the null hypothesis, right? And so in order for us to conclude that the null hypothesis is not actually true, that the data support the alternative, the level of significance tells us how much evidence are we actually requiring for that. Lower values for alpha require more evidence, right? And so it's sort of this inverse amount of evidence that we need there. So smaller values represent a need for stronger evidence, and conversely, larger values represent less required evidence. Okay. The value of alpha needs to be catered to the specific scenario. So if we're thinking about the different ways that we might apply hypothesis testing, right? There are scenarios that are very important, and there are scenarios that are going to be a lot less important. So you can think about, on one hand, we have life or death scenarios. On the other hand, we have mere curiosities. And of course, the things that are life and death, we require a lot stronger evidence to make sure that we're not making mistakes, or at least be a lot more certain that we're not making mistakes. If we have something that's really just a curiosity, well, if we make a mistake, the stakes are quite low, right? And so this amount of evidence that we're actually going to need is going to depend on the actual claim that we're making, right? Where when you have more extraordinary claims, you're going to require stronger evidence to support them. Okay, so some situations are going to depend on stronger evidence or require stronger evidence in order to draw the same conclusions. Okay. Now, despite the fact that the level of significance should be selected on the basis of the scenario that we're looking at, there are some common default values that are often selected across different fields. And so the most common that you're going to see is taking alpha to be 5% or 0.05, but alpha equals 0.1 or alpha equals 0.01 are also both very common. And so if you're working in a field, you're very likely to see everyone is using one of these three values, regardless of what they're testing. Whether they're testing something that matters a lot, or if they're testing something that doesn't matter at all, they're going to be picking from one of these three values here. My opinion is that these default values should be avoided wherever it's possible. Of course, when you're working inside of a system and you're doing science within that system, you might have to work within sort of the defaults of the field that you're in. And in that case, of course, go ahead and do sort of whatever is necessary. But whenever you get the choice, you should really be thinking deeply about, well, what value of alpha is going to make sense here? Sometimes 5% might make sense. Sometimes 1% might make sense. Sometimes you're going to want it to be a lot smaller, right? Maybe 1 in a million. Maybe you really, really want very strong evidence in a claim. Other times you might not care as much, and maybe you're willing to take, say, alpha is equal to 0.2, right? Which would be a lot less evidence that's required in order to draw the same types of conclusion. And so the level of significance should really be selected not on the basis of statistical considerations directly, but from the scenario that arises. However, thinking about the level of significance as just the amount of evidence required to reject the null hypothesis, it can be difficult to pin down a specific value for it. And so it's useful for us to think about, is there another way that we can frame this value of alpha? Okay? And in order to do so, we're going to talk about errors within the hypothesis testing framework. So because there is sampling variability, it is not possible for us to be certain in any conclusions that are drawn within the hypothesis testing framework. Right? We can't be 100% sure that we're drawing the correct conclusion, no matter how much the data seem to support it. Right? It's always possible that we have just a very weird sample, and that very weird sample is leading us to draw the incorrect conclusion. Now, there are two ways that we can be wrong within hypothesis testing, and that's because there are ultimately two conclusions that we can draw. So the first, which we call a type 1 error, happens if we reject the null hypothesis when it is actually true, right? And so we call this a false positive, or refer to it as a type 1 error, right? And this is going to happen if you have enough evidence to reject the null hypothesis, but in the real world, the null hypothesis turns out to actually be true, right? So we've said the data don't support the null, but the null actually turns out to be true. That's our type 1 error. It's a false positive. The type 2 error is going to be when we fail to reject the null hypothesis when it is actually false. So we say there's not enough evidence to reject the null hypothesis, but it turns out that the null hypothesis is not actually correct. So this is also a false negative because we didn't find a significant result. We called it a type 2 error, right? And so type 1, type 2 error depend on the type of conclusion that is actually being drawn. If you reject the null hypothesis, you risk making a type 1 error. If you fail to reject the null hypothesis, you risk making a type 2 error. Okay. There's always going to be some positive probability that either a type 1 or a type 2 error will be made. Any test that gives you a 0% chance of making a type 1 or a type 2 error is not going to be a useful test, right? And so there's always some chance that we're going to make one of these errors, depending on the conclusion that we draw. And so when we're thinking about trying to select level of significance, when we're thinking about trying to calibrate our tests, what we're really thinking about is how can we control the type 1 and the type 2 error, and sort of moreover, which of these is going to be more important for us to control, right? So trying to balance out these sources of error is going to be an important component of actually doing valid hypothesis testing. And the thing that you could think about here, right, is if we think about sort of our hypothesis test in, say, the criminal proceeding setting, right, where you are trying to make a decision as a jury, right, and either you can convict someone or you can say that there's not sufficient evidence to convict them, right? You don't find them innocent in this case. You are saying we're either going to convict them or we're not going to convict them. We're going to reject the null hypothesis or we're going to fail to reject the null hypothesis. And in the criminal proceeding, if you have a false positive, this would be when you have convicted someone of the crime that they did not actually commit. And a false negative is going to be you fail to convict someone of a crime that they actually did commit, right? And so then in the criminal proceeding case, we typically would say that a type 1 error is going to be worse, right? It is worse to find someone who has guilty of a crime that they did not really commit, to punish them, to make them serve a prison sentence if they're actually innocent. We find that to be sort of an unacceptable situation. And so in the criminal proceeding case, we tend to try to minimize our type 1 error. But there are going to be other situations, and we'll see some of those later on, that maybe you actually want to control the type 2 error instead. Okay. So for the following examples, what we'll try to do is just identify in words corresponding to the given scenarios, what do a type 1 and type 2 error actually represent? So in the first scenario, we have researchers developing a new pesticide, and it's meant to be harmless to the populations of bees. So they're running a study to detect whether or not the bee colonies exposed to the pesticides are harmed or not. And in this case, their null hypothesis is that there is no impact on the health of bees, right? And so we have to think, in this case, what is going to be a type 1 and a type 2 error? And the type 1 and type 2 error are always going to be defined based on our null hypothesis here, right? So the null hypothesis is that there is no impact on the health of bees. Remember, a type 1 error is a false positive, so you've rejected the null hypothesis, but it turns out to actually be true. A type 2 error is a false negative, so you fail to reject the null, but it turns out that the null is actually false. So if we reject the null hypothesis, then we conclude that there is an impact on the health of bees, right? So we would be concluding that there is an impact on the health of bees, but if that's a false positive, then in fact, there actually is no impact on the health of bees, right? So the type 1 error here would have them conclude that there is an impact on the health of bees when in fact there is not, right? So we said, yes, this pesticide actually harms bees, but turns out the pesticide is actually fine for bees. A type 2 error is going to have sort of the opposite conclusion here. So we're going to conclude that there is no impact on the health of bees, but it turns out that there really is, right? So a type 2 error would have us conclude that there is no impact on bees when in fact there is. So that's a false negative. Okay. Our second scenario here, researchers are developing a treatment for a rare, extremely dangerous disease. There is one present alternative for treatment right now that works. The null hypothesis here is that the treatment does not treat the disease effectively, right? And so the treatment is not effective is our null hypothesis. So we have to think, okay, well, what's a type 1 and what is a type 2 error? The type 1 error is going to come if we reject the null hypothesis. And in this case, if we reject the null hypothesis, we say the treatment does treat the disease effectively, right? So in that case, we're treating the disease effectively. But if it's a type 1 error, then the actual truth is that the null was correct. So the type 1 error in this case is going to be we conclude that we treat the disease effectively. However, that is not actually the case. The treatment does nothing, right? So type 1 error would have the researchers conclude that the treatment is effective when in fact it is not. The type 2 error is going to have us drawing the opposite conclusion, right? So we're going to conclude that the treatment does not affect the disease effectively, or does not treat the disease effectively. However, it actually does, right? So a type 2 error is going to be, we conclude that the treatment is not effective when in fact it is actually effective. Okay. The third example here, we have a company that's interested in conducting market testing prior to the launch of their new product. And what they're going to consider is the null hypothesis that the new product will not be profitable. Okay, and so again, type 1 error, we're going to reject that null. So we'll conclude that the new product will be profitable. However, in truth, it will not be profitable, right? So type 1 error, have them conclude that the new product will be profitable when in fact it will not be. The type 2 error, we draw the opposite conclusion. So we conclude that it's not going to be profitable when in fact it will be, right? So the type 2 error has them conclude that there will not be profit made with this product when in fact they would have. Okay. One last example here. A government agency is piloting a new program designed to reduce poverty rates in a region. The null hypothesis is that the program has no effect on poverty rates. So again, a type 1 error is going to be if we reject that null hypothesis. So we conclude that there is an effect on poverty rates when in fact there is not one. Right? So if we conclude that it has an effect, but there isn't, that's a type 1. It's a false positive. The type 2 error is going to have us conclude that there is no effect when in fact there actually is some positive effect, right? So whenever we're faced with these scenarios, the type 1 error always arises from us rejecting the null when it's true. The type 2 error always arises from us failing to reject the null when it is false. We can explore the types of errors sort of in more depth here. So with type 1 errors or false positives, in general, these are going to be the errors that we actually directly are controlling within the hypothesis testing framework. Okay. And specifically, the way that we do this is by noting that the probability that we make a type 1 error is exactly our level of significance. So another way that we can think about alpha is alpha gives us the probability of a false positive. It gives us the probability of making a type 1 error, right? So alpha is the probability that you reject the null hypothesis when it turns out that it is actually true. So the probability that the null hypothesis is rejected, given that it's actually true, is equal to alpha. And if we think about that sort of intuitively, that's going to make sense based on how our hypothesis testing is defined. Whether we're using p-values, where your p-value has to be less than alpha, or you're using critical values, where you have to be outside of those alpha thresholded values. In both cases, we say, well, there's an alpha probability chance, assuming that the null hypothesis is true, that we would observe something at least this extreme, right? Or at least there's a below alpha chance of that. And as long as there's at least an alpha chance of that or less, then we reject the null hypothesis. And so there's alpha probability that the null hypothesis is rejected, given that it is actually true. Okay. So in order for us to select an appropriate level of significance, we should be giving consideration to the acceptability of a type 1 error, right? And so how acceptable is a type 1 error? Because the alpha level is the probability that you make a type 1 error. So what is the acceptable rate of false positives in the given setting? And for different settings, this is going to be a different value, right? If we think back to the criminal justice example, right? In the case of a criminal justice, a false positive is such a bad thing that we really want there to be no reasonable doubt, right? And if we tried to assign a probability to that, that might be a little bit hard, but we want there to be basically no chance that we're doing this. There are other times where making a false positive really isn't going to have a major impact on us. And so in those cases, we might be able to get away with taking alpha to be slightly higher. Now, there is an interesting question for us to ask ourselves, and that's why do we not take alpha equals 0? Because in some sense, the rate of false positives we would ideally like to be 0. And if alpha is just the probability of making a false positive, then we could take the probability of that and set that equal to 0. And the problem is that the only way that you can get alpha equals 0 is by never rejecting the null hypothesis, right? If you never reject the null hypothesis, you're never going to find a false positive because you never find a positive. But if we're never going to reject the null hypothesis, then there's no point in doing hypothesis testing. And so the problem is, as soon as you want to actually be able to draw conclusions, as soon as you want to be certain, right, we can't make useful conclusions because the uncertainty is inherent in this. There's sampling variability. We can't escape the uncertainty. And as a result, there's always going to be some chance of making a false positive so long as we're actually doing useful hypothesis tests. Okay. Now, the other important thing to note is if we can't take it 0, why don't we just always make it as small as possible? And the reason for this is because there's going to be an inherent trade-off between the probability of a type 1 error and the probability of a type 2 error. Okay. So if we reduce the probability of a type 1 error, we're typically going to be increasing the probability of a type 2 error and vice versa. And so because of this, we have to be thinking, well, does a type 1 error matter more or does a type 2 error matter more? Because if we shrink too much the probability of a type 1 error, then we've increased the probability of a type 2 error. And if we do that, then we have to be saying, well, we care less about the type 2 errors than we do about the type 1 errors, right? And if the opposite is true, then maybe we want to increase the probability of a type 1 error, right? So there's always this trade-off. And so because of this, we should think about type 2 errors. And when we're thinking about type 2 errors, we're also going to introduce this concept of power into hypothesis testing. So type 2 errors or false negatives, they're typically going to receive secondary consideration from us. So we select alpha that controls the type 1 error rate, and then we're looking for the test that's going to minimize the type 2 error, right? But when we're selecting alpha, we have to note that selecting too low of an alpha is going to make the probability of a type 2 error increase. Okay, so the probability of making a type 2 error, we denote with beta, right? So the second letter there, alpha for type 1, beta for type 2. And oftentimes, instead of thinking about beta directly, we're actually going to think about 1 minus beta, right? And so the complement probability. And if we're thinking about, well, what's the complement of a false negative? The complement of a false negative is a true positive, okay? And so as a result, 1 minus beta is going to be the probability that we reject the null hypothesis when the null hypothesis is actually false, right? So we've done a true rejection of the null hypothesis. And in some sense, that's the probability that we care the most about in our hypothesis testing. What is the probability that we find a result that we say, you know, the null is not actually true here, right? We've rejected the null and we are right. That is sort of how good is this test. Okay. Because that's such an important probability, we actually refer to this as the power. And so the power is the probability that the null hypothesis is rejected when it is actually false, right? So a higher power is going to be better because that means we increase the probability that we're rejecting the null anytime that it is false. The power of a test is given by 1 minus beta, right? And so instead of thinking about type 2 errors and beta directly, we're normally going to think about the power of the test instead. Okay, so we want the power to be as high as possible. And so ideally, in sort of a perfect hypothesis test, we would have as small of an alpha as possible and as high of a power as possible. Unfortunately, as we decrease alpha, beta is going to increase and vice versa, right? And so there is this trade-off between alpha and beta here. And so we need to be balancing those two factors. Okay. So in order for us to balance those factors, we should really be thinking about, well, does a type 1 or type 2 error matter more? And so we'll go through those same scenarios we were looking at before and try to decide which is more important, having fewer type 1 or fewer type 2 errors. Okay, and so this first example, again, has us thinking about this new pesticide, and we're trying to determine, is it harmful to bees? The null hypothesis is that there is no impact on the health of bees. And so we're asked in this case, is it worse for us to conclude that there is an impact when there isn't, or that there is no impact when there actually is? And in this case, of course, it's going to be worse for us to say, no, this pesticide is totally safe if it's not actually safe, right? So a type 2 error here is going to be worse. In a type 2 error, we're going to be harming the bee populations when we think that they're actually safe for the bees, right? That's a worse outcome than if we say, no, this isn't a safe pesticide, and then it turns out that it actually was, right? As a result, we want a higher power here, or a lower type 2 error rate, in order to avoid those type 2 errors. And we can sacrifice some type 1 errors. We can say it's okay if we don't necessarily find an effective pesticide here, as long as we don't say this pesticide is effective if it's not actually. Okay. Our medical example here, right? Remember that this is treating a disease that there already exists one alternative treatment for, right? So there is already one treatment that works. And our null hypothesis is that the treatment does not treat the disease effectively. So we have to think, is it worse for us to conclude that it does treat the disease effectively if it actually doesn't? Or is it worse for us to conclude that it does not treat the disease effectively if it actually does? And in this case, the key piece of information that we need to be thinking about is the fact that there already is one treatment that works. Okay? Because there's already one treatment that works, this actually changes our thoughts here. Because if we make a type 1 error here, then we're going to say this is an effective treatment when it turns out it's actually not. And if we think about what's going to happen there, some people are going to receive that treatment when they could have actually received something that actually worked. And so here a type 1 error is going to be worse, right? Type 1 error here is worse because that would have us using this treatment when it is not effective, and that perhaps removes people's ability to receive the already existing effective treatments. So we should be reducing alpha in this case. If we were to say, instead of at present, there's one alternative that actually works, if we were to say there is no treatment alternative that works, then in that case, we would probably prefer to minimize the type 2 errors. Third example, we're thinking about this company launching a new product. Their null hypothesis is that the new product will not be profitable. So my first thought here is that a type 1 error is likely worse because that would have us launching an unprofitable product thinking that it's going to be profitable. You end up losing money. That's not great, right? And so in that case, alpha should be reduced. However, in this case, you could also make an argument that a type 2 error might be worse, right? So depending on the context of the firm, it's possible that a type 2 error would be worse, where the type 2 error has them not launching something that would have actually been profitable. So if you imagine a company that's already sort of struggling, missing out on a profitable product might be a worse outcome than launching a product that is not profitable, right? And so in this case, it's going to depend on the context of the firm. You could make an argument for either of those being worse. The final piece here is we're thinking about this new policy. The null hypothesis is that the program has no effect on poverty rates. So again, this is going to be sort of a judgment call, but in my opinion, a type 2 error is going to be worse here because that would have us removing resources from an effective program. That would have us saying, no, we don't think this program is actually effective, but it turns out it is. And so then we have avoided helping people sort of in need of resources from the government. And that sort of feels like, skirting the responsibilities of the program more so than saying we think the program's effective. It turns out it's not effective and sort of wasting some resources there. Okay. So to sort of summarize this all in a given table, right? There are two different types of conclusions we can draw. We can have that H0 is rejected or that it is not rejected. It's failed to be rejected. And then there are two truth values, right? Either it's true or it's false. If we reject H0 and it turns out to be true, then we've made a false positive. That's also a type 1 error, and that happens with probability alpha. If we reject H0 and it turns out to be false, then that's a true positive. We call that the probability of that happening the power, and that's given by 1 minus beta, right? And so that's if we make the decision to reject the null hypothesis. Alternatively, if we have failed to reject the null, so we do not reject the null, and it turns out that H0 is true, then we've made a true negative. We don't normally think about this case very much. It would have probability 1 minus alpha, but that's not particularly important to us here. More important is going to be if we do not reject it but it turns out that it is false, then we've made a false negative. Okay, that's a type 2 error that happens with probability beta. Right, and so then this table right here gives us sort of the types of conclusions that we can draw and how these are balanced out. Remember that as we decrease alpha, we're going to typically have to increase beta and vice versa. And so there's going to be always this balancing within sort of the outcomes on this table here. So whenever we're drawing conclusions from a hypothesis test, both false positives and false negatives need to be considered. The level of significance is then selected to control the rates of false positives. So to go back to what we were chatting about at the beginning, when we're trying to select the level of significance for a hypothesis test, we really need to be thinking about this on the basis of what conclusions do we need to draw, what is acceptable for us to conclude, what is unacceptable for us to conclude, rather than just defaulting to the values that are commonly applied, right? And by selecting a level of significance that's going to control the type 1 error rate at a sort of relevant value given the context, then we're going to be able to trust the results of our hypothesis test a whole lot better, and the conclusions that we draw are going to be a lot more supported by the processes that we've actually followed.